Hello everybody. Let me welcome you to our lecture dedicated to differentiation. In our lecture, we will study the derivatives. We will start with definition of a derivative. We will talk about the slope and the rate of change. We will talk about tangent line. We will look at the constant and inconstant slopes, and then we will study how to calculate the derivatives. We will study the differentiation rules, and then how to find the derivatives of polynomial functions and the derivatives of exponential and logarithmic functions. And then we will talk about what we can study more. Let's look at this example. Since we are dealing with quantities that are changing, it may be useful to define what that change actually represents. Suppose we have an eccentric pet ant which is constrained to move in one dimension. The graph of its displacement as a function of time is shown below. So we can see our blue curve that represents our function x of t. At time t, the ant is located at point A, so its position is described by our coordinate x of t. At time t plus delta t, our ant is located already at the point B, and our position is defined by the coordinate x of t plus delta t. Let's suppose we have a second line which is drawn through the points A and B. We can note that the slope of the second line is equal to the rise over the run. So our slope equals the difference of x coordinates over the difference of t coordinates, and this equals x of t plus delta t minus x of t divided by t plus delta t minus t. And we can exclude our t from our denominator, and finally we obtain our x of t plus delta t minus x of t divided by delta t. Let's draw a tangent line to our blue curve. Our blue curve is our function, right? So here we can see our red straight line, and let's do the following process. We will hold a point A fixed while allowing delta t to become smaller and smaller, and this means that our point B will move towards to the point A by the direction defined by this green arrow. So our point B becomes closer and closer. And if we will continue and zoom in at the point A, we can see that our function curve appears straight, and our green line will become closer and closer to our red line, and this means that we assume that our second line becomes a tangent line. In one hand, we have defined a slope of the second line, which is equal to x of t plus delta t minus x of t over delta t. In the other hand, we defined the slope of tangent line when we allowed our delta t to become smaller and smaller. It means that we take the limit, so the symbol lim stands for the limit, and this limit shows the delta t approaches 0. As this happens, this fraction approaches a finite number, and this actually is a derivative itself. So our derivative yields a new function that defines the rate of change of the original function with respect to one of its variables. In our example, we see the rate of change of x. which is the position with respect to time, and this is the velocity of our path end. If our function is represented by a straight line, like here where we have a distance versus time, we can see that our slope is constant. It means that our velocity is also constant, and here it is calculated and equals 40 kilometers per hour. If we continue to study the distance versus time, we can have several cases. For example, in this case, is already known. We said that we have constant speed and our derivative in this case is greater than 1. Also, we can have this function, and this means that we have accelerating speed and our derivative is a function of time. Also, we can have this function, and this means that we have decelerating speed and our derivative is also the function of time. And finally, we can have this function, and this means that we have constant speed, but our speed is slow, and our derivative is greater than 0 but less than 1.